Hello, everyone. Hope you're doing well. Here in a new location for a new video where we're talking about completions. Now, the completions we're going to be talking about here are with respect to metric spaces. We've talked about how there are some spaces that you can say are not complete. In fact, I believe we've gone through a theorem already that says that whenever you have a complete space, your space must be closed. Because recall, for a complete space, Cauchy sequences must converge. And recall that a closed set is something where limit points are inside of the set. That is, if something is the limit of a sequence of points inside of the set, well, then the point itself needs to be there inside the set. Otherwise, it would not converge inside of the set. An example of a set as a subset of the real numbers that is not complete then would be like the open interval from 0 to 1. And the reason is you could take a sequence like 1 minus 1 over n as n goes from 2 to infinity, which is a sequence of elements that is inside of the open interval going from 0 to 1, but no limit point exists for this sequence inside of the set. Now, you might say, John, well, if I had just extended my open interval one more number, then I would have something that is a limit point. So doesn't that count for something? Well, for saying something converges in a set, we are saying that not only are all of the points inside of the set, but that the limit point itself is also inside of the set. So this kind of tells us we would need the point 1 in our set in order for this sequence to converge. And similarly, because of the sequence 1 over n as n goes from 2 to infinity, we would need the point to 0 as well. Now, the closed interval from 0 to 1 is a complete set. All Cauchy sequences inside of this interval converge inside of this interval. But note even a small change to this interval, something like this, taking the interval from 0 to 1 and intersecting it with the rational numbers, again makes this incomplete. And that's because you can now take a particular sequence of rational numbers, Qn, that converges to something like, say, the square root of 2 over 2. We know that something like this exists because the rational numbers are dense inside of the real numbers. And we'll be talking a little bit more about density today. But the square root of 2 over 2 is an irrational number, so it does not exist inside of this set. However, the rational numbers that would converge this number are Cauchy inside of this interval. So this is an example of a Cauchy sequence that does not converge. So these are two examples of incomplete spaces and an example in the middle here of a complete space. But you could see what we would need to do to add to this set to make it the smallest set that is complete that contains all of its intervals. In each of these examples that I'm giving here, the completion of this set would be the closed interval from 0 to 1. That would be the completion of each and every one of these sets that's given here. So that's what we'll be talking about, is how we can construct a completion for something that's not just the real numbers. What if I have something like the q to the n, say the set of all n tuples coordinates of numbers where each particular entry is a rational number. If you try and visualize what this might look like, you might also see, similar to how the rationals fit inside of the reals, a space with a lot of holes in it. Well, whenever you make a completion, you might gain infinitely many more elements, and more than that, just a completely new cardinality set of numbers more than what you had to start with. The rational numbers being countable, same thing as q to the n being countable. But similarly, the completion of this one, the completion of q to the n is r to the n, an uncountable set. So a completion might be extremely large compared to the set that you're starting with. Think back to like things like the closed interval 0 to 1 intersected with the rational numbers, but also note that the open intervals from 0 to 1 to the closed interval from 0 to 1 only added 2 points. So there's a little bit of trying to deal with the nature of what it is you're starting with and then saying, okay, well, how can I make sure that whatever I'm getting, all Cauchy sequences from the original set converge inside of what I call the completion of that space? And what's more, something that will be interesting to discuss is that this completion here is going to be unique up to a particular property. So we'll talk about that near the very end of today. So as we do this, keep in mind that we're thinking of trying to take something like the rational numbers and making them into the real numbers. We've already discussed briefly what that kind of completion looks like. We've discussed that it is the set of all Cauchy sequences quotiented out by an equivalence relation. And that's exactly what we're going to be doing in the general metric space examples that we talk about today as well. If you need to go back and check to see where we mentioned that briefly, it was video lecture 2-2, where we started talking about these relations. Remember that in chapter 1 of our textbook, we have a little bit of a treatise on how a relation works. In particular, an equivalence relation is something that satisfies a few different properties, which we'll talk about in the next slide. And the equivalence relation induces a partition of the number by which you can quotient out to get the set of equivalence classes. Now, to be clear, we don't want to be taking our completions to be too big. For example, if we could take the open interval from 0 to 1 and say, oh, its completion is the entire real line. But that seems to be a little bit too big for our tastes. The open interval 0 to 1 doesn't even stretch along the entire real line. It is a complete space that contains the open interval from 0 to 1, but it's too big. So we need to ask the question, how do we determine if the completion that we're working with is indeed the right size for the set that we're starting with? And to do that, we introduce this notion of density. Now, to say something is dense is like this. Let's say that we take open intervals around any of the points in our original space, and I'll use Q here as an example. Take an open interval in Q. Well, open intervals in Q consist of entirely rational numbers. Our way of thinking of this in terms of the real number line is that if you take a rational point and look at its open interval, you're getting all of the rational points that exist inside of that open interval. Now, what happens if I consider an open interval in the completion of Q? What happens if I replace this with R? Well, now that I have this same sort of picture that I've been looking at, notice that I have an open interval here on the real number line. And what's more, the rational numbers are always contained within any open interval that I do. There's at least one rational number inside of every open interval that I can construct on the real line. That's exactly the definition of density. So the sequential definition is what is given down here, but I'll explain it in terms of the open and closed sets that we've been working with. We could also say something is dense if the closure of a set is equal to the set, is equal to the entire completion of that set. Let me actually change this definition just a bit because it is currently saying that just that the set is closed. Here we go. I've changed it now. It's to say that the closure of the dense set is the entire space. So we would say here, if we had something of this form, that D is dense in X. That means the closure of the set D is all of the things inside of X. So how does that relate back to our open sets definition? We'll say that the closure of D is not equal to X. Well, what does it mean to be closed? That the complement is open, right? Well, let's say, for example, that the closure of D is not the entire space. Well, what that would mean is that X complement the closure of D would be something that is not empty. In which case, what would you have? You would have an open interval because you are looking at the entire space and complementing it out by a closed set. This is an open space. Oops. This set is open. And you would have an open set that contains nothing of the original dense set that you're working with. In fact, it contains nothing of the closure of the set of D that you're working with. So if you can imagine an open interval that has nothing of the rational numbers, then you would be saying, okay, well, that open interval is inside of this set. It's outside of the closure of the rational numbers. But that's not something that's true. Every open interval in the real numbers contains a rational number, in which case what you could say there is that the closure of the rational numbers is equal to the entire real line. Here we are taking our closure with respect to being inside of the completion, the rational numbers kind of being dispersed throughout the real numbers here. Taking its closure means taking the limit of all possible sequences as well. So we can think of this in a sequential definition. And remember that for any irrational number, you can construct a set of rational numbers that get to it. We talked about this with square root of 2. You could take things like 1, 1.4, 1.41, a sequence of entirely rational numbers that gets us to this irrational number. In fact, when it comes to our completion, we're going to be calling the square root of 2 this Cauchy sequence in the rational numbers and use that as a construction of the real numbers. Again, maybe that helps kind of conjure that memory up for you for what we do in the reals. So this is our notion of density. It's saying that the set that you're starting with is dense in the entire set that you're constructing. Any open interval that you might construct inside of the completed set is going to contain something inside of the set that you're completing, the set that you're starting with. That's why we can't say, for example, that the completion of the open interval from 0 to 1 is all of the real numbers, because there are plenty of open intervals that never intersect the closure of this set, open interval from 0 to 1. So that's going to tell us when we have a good completion, is that the set that we're starting with is snugly fit in there and just to the right size. This in some sense says we have the smallest possible complete set that contains these intervals, because we know complete sets have to be closed. So that's exactly how we're going to define a completion. We're going to ask for it to have two conditions. We're going to ask for a completion of a metric space such that, one, that you have something that is a subspace of X bar. So that is, for example, that X is inside is as a subset, and the distances are indeed the same between any 2 points inside of our original set here. Here I should be saying that this set X is what we have right there. So the distance with respect to X bar is going to be the same as the distance for X. So for example, when I complete a space, 2 points don't suddenly become closer together or farther apart. And two, we're going to ask that X be dense inside of X bar. So notice that these two conditions tell us two different things. One tells us something about the set of it. So this is saying that as sets, one is contained within the other. And this one also says that the metrics are extensions of what you had from the original set X. So you're extending the metric of X to the metric of X bar. And the second one tells us something about the topology of it. It tells us something about sequences and their convergence, open and closed sets. This tells us that X is dense inside of X bar, that there's a closeness, a snugness to the fit of how X bar works with respect to X. So for this definition, we'll be utilizing an equivalence relation. Since we haven't talked a lot about equivalence relations in our video lectures, we have seen them in our reading, again, back in chapter 1. I'll go through and talk a little bit about an example of an equivalence relation to refresh our memory. The rational numbers, for example, have a natural equivalence relation that we inherently use when we talk about rational numbers. The question is, why do we not consider 1/2 and 2/4 to be the same? Well, 1/2 and 2/4 in terms of real numbers in real world, these automatically come to us as the same. If I take a pizza and I divide it into halves, and I take another pizza and divide it into fourths, and then I take a look at 1/2 of the first pizza and 2/4 of the second pizza, then I know that I'm looking at the same quantity of pizza, either direction, either pizza that I'm working with. And there's an inherent, just like visual kind of thing that kind of helps us there. So how do we understand that and translate that algebraically? Well, what we do is we use an equivalence relation. We say, okay, well, what's happening between 1/2 and 2/4? Is it the case that these two things are equal? Well, something that we do sometimes in working with this in terms of our students is we say, okay, well, let's take this and cross multiply. Top left number, top number in the left fraction and bottom number in the right fraction. Multiply those together. You get 4. And is it true that this is equal to taking the top number in the right fraction, multiplying it times the bottom number in the left fraction? Is it true that 4 is equal to 4? The answer is yes. So we say that 1/2 equals to 2/4. And in fact, that's exactly how we algebraically make sense of it. We say that these two fractions are equivalent if the cross multiplication works out. Now, that's just a definition of this equivalence relation. This is, by the way, an equivalence relation. Remember that an equivalence relation has 3 things to it: reflexivity, symmetry, and transitivity. You can see the definitions of each of those here. One of which says that every element is related to itself inside of the set. For example, AB needs to be related to AB. And that's true, since if you do the cross multiplication, you have AB on both sides. Then you need, if whenever X is related to Y, then Y is related to X. The order does not need to matter whenever I construct a equivalence relation. Well, AB is related to CD. That means AD equals BC. But because the equality relation is symmetric, we have that CB equals DA. Notice I'm also using some commutativity here to get this into exactly the same form that I need it to be, which is CD is equal to AB. Note that I'm able to go from this step to this step because all equivalence relations are ifs and if and only ifs. Meaning if these two fractions are related, then they satisfy this equality. And if they satisfy this equality, the two fractions are related. And then finally, if A over B is related to C over D and C over D is related to E over F, what I need to be able to say is that due to transitivity, A over B is related to E over F. So what I do is just a little bit of kind of what we might call in the business pushing pencils. We are going through and attempting to just get to that formula using certain substitution. And you can see how I go through and do these substitutions to eventually get that AB is indeed related to E over F. This should not be a surprise to us, as this is like saying 1/2 is related to 2/4, 2/4 is related to 4/8, so 1/2 is related to 4/8. Equivalence relations are exactly the type of relations where everything related to each other could be set equal in a well-defined set theoretic way. That means as a set, we could quotient out by this and get something where everything inside of a particular equivalence class, that is the set of all things that are equivalent to each other, is considered equal inside of that set, that they're all boiled down into one element in what is known as a quotient space. So equivalence relations induce what are known as partitions on our set. These are disjoint unions of sets. Here, this kind of symbol means disjoint union, which forms equivalence classes. So when I think of the rational numbers, I don't think of 1/2 and 4/8 as two separate elements. I don't, because due to the equivalence relation that I put on the rational numbers, what I'm doing is I'm saying, okay, well, I'm going to consider 1/2 and 4/8 to be equal elements. So when I reference 1/2, I might be referencing something called the equivalence relation of 1/2, and I might write it like this. What that means is I'm looking at all of the elements, not just formally equal to the number 1 placed over the number 2. I'm also considering all possible elements that are equivalent to that underneath the equivalence relation. For example, 2 over 4 is equivalent to it, 4 over 8 is equivalent to it. So I'm considering all of those elements at once when I write this particular set. Now, you know that when we work with the rational numbers, we typically will just write this equivalence class as just 1/2 in order to simplify the notation. But whenever it needs to be made clear, we will put brackets around the 1/2. This is typically how we work with the rational numbers. In fact, when we usually write the rational numbers, we usually write it without that equivalence relation as well. And so to give the most formal definition of the rational numbers, we say that it is formally all m over n, where m is an integer and n is a natural number, quotiented out by the equivalence relation that we have just been studying. So this is the example that we're starting with. We start with an equivalence relation here on the rational numbers, and we're going to need that construction of an equivalence relation in what is to come. So I start with the rational numbers to get us started with seeing, okay, how can we work with this in a general metric space? One thing that's important as we do this is that our operations with the rational numbers also be well defined. For example, maybe I could find another equivalence relation that happens to work with the rational numbers. Maybe I put a 2 somewhere inside of the AD equals BC relationship. AD is equal to 2 BC, for example. But at that point, I have to ask a few questions. I also need to say, okay, from a set theoretic perspective, that's all well and good, but what if I start adding in operations? For example, if I take a look at 1/2 plus 1/3, do I get something that is well-defined as an addition? Remember, we've already gone and talked about well-defined in terms of functions. We would say a function was well-defined if writing a function in two different ways, or writing an x value in two different ways, still gave us the same y value whenever we went through and plugged that in. Now, this might seem like something that's obvious, but it's not quite obvious when it comes to equivalence classes, because you could pick two different elements that represent the same equivalence class, and potentially, if you're not careful with how you define your function, it's not something that's well defined. An example of a non-well defined function in terms of the rational numbers would be something like this. Take a function that takes a rational number m over n and just return its numerator. This is a function that is not well defined because it begs the question, how are you writing the number 1/2? If I write the number 1/2 as, well, 1 over 2, then what this function gives me is 1. But f of 2 over 4, that's equal to 2. Here, 1/2 is equal to 2/4 with respect to our equivalence relation. However, these two things are not equal. So this is an example of a not well-defined function for this. And we have to do the same thing when we consider the addition function. Remember, the addition itself is itself a function. It's something that takes a rational number cross a rational number and gives us a rational number back. If I put two numbers inside of an addition operation, it's supposedly given me the sum of those two rational numbers. So if I take something like 1/2 and 1/3 and consider their addition, I need to make sure that when I map this to the number 5, 6, that that's something well defined. What if I had plugged in 2/4 or 3/9 for these two numbers respectively? Would I get something that still works for the addition, the method of it? For example, the whole middle schooler or fifth or sixth grader's dream of taking something like 1/2 plus 1/3 and getting something like 2/5, this is not a good definition. Just adding the numerators and the denominators does not give us a well-defined addition operation, because I could have written 2/4 and 3/9 and gotten something that's not equivalent to the original number that I had. So this is an example of a way of defining addition that's not well defined. Gratefully, our notion of addition is well defined, and that's essentially why we use it. But that's something that we need to be keeping in mind as well as we go through this. You'll see that once we construct this particular set that we're working with, that we go through quite a few conditions to ensure that this set is the thing that we're looking for when we talk about the completion of a space. So we're going to want to have addition operations and other things as well. You'll see in our homework, we're going to go through a little bit of a paper that talks about how completing the rational numbers to make the real numbers still gives us well-defined operations as well. Let's talk a little bit about this problem right here, just kind of getting an idea of how we might start looking at these completions. Let's take a metric space, x comma d, and let's let this kind of squiggly x be the set of Cauchy sequences on x. So for example, if I'm looking at x being the rational numbers, then the squiggly x is going to have something like the number. It's going to have something like the element in it, 1, 1.4, 1.41, so on and so forth. It will have these elements inside the set of Cauchy sequences. Let's show that this is a relation, or an equivalence relation to be precise. If that's, we'll say that two Cauchy sequences are related to each other if the limit of the distances between those two sequences goes to 0. Now, notice we don't say anything about what happens when the two sequences don't have a limit of 0. We're going to say that those two things are separate, even if the two end up, say, diverging. But what we will say is that when the limit of the distances between corresponding points inside of that sequence go to 0, then that's an equivalence relation. A quick example of this before we move on, we might look at two elements of x like this: 1, 1.4, 1.41, 1.414. I keep using the same types of examples, and I hope you don't mind for that, but it's helpful to just make sure that I'm focusing on the right things here. Then we might consider 2, 1.5, 1.42, 1.415, so on and so forth. Think of this as approaching the square root of 2, one sequence from beneath, one sequence from above. Notice that the difference between these two elements, if I take xn and this to be yn, then the sequence x sub n minus y sub n is equal to the sequence 1, 0.1, 0.01, 0.0011, excuse me, and that this sequence clearly does converge to 0. So we would say that these two Cauchy sequences are equivalent. So our reason for thinking about this example to begin with is that it seems as though these two Cauchy sequences, if they converged to the same point, which in the rational numbers they don't, if they converge to the same point, then they would be considered the same element and with respect to this equivalence relation once we quotient it out. But to do that, we need to ensure that this is indeed an equivalence relation. So why don't we go through and check that out? Let's see if we can show that this is an equivalence relation. First, we need to be able to show that x sub n is related to x sub n. We need to, that this is only true whenever we say, okay, well, if you take the distance from x sub n and x sub n, take this limit here, is it true that this limit as n goes to infinity is equal to 0? Is that true? Well, in fact, yes, because in fact, for all n, dxn, xn is equal to 0, which implies that the limit as n goes to infinity of this sequence is equal to 0. Now that looks like a very straightforward example, and I'm glad for that. That helps us know, okay, we're getting in the right direction. The second thing is, due to the fact that the metric is symmetric, we could see that xn is related to yn in terms of sequences. Xn is related to yn. This implies that the xn comma yn. This limit is equal to 0. But the same thing is going to be true even if we try and switch the two coordinates. And the reason is we're going to get something that's true because dxn yn is equal to dyn xn. And that's due to the symmetry of any metric that we choose. So the limit as n goes to infinity of dyn xn, that has to be equal to 0 as well by the fact that these two sequences are term by term the same. And remember that this means that, by definition, yn is related to xn. Our third condition, which I have unfortunately run out of room here to talk about, that third condition is saying that if xn is related to yn and yn is related to zn, then we need to say, is it the case that xn is related to zn? The answer is going to be yes as well. And I want you to think a little bit as to why. Why is it the case that this ends up working? Remember, we want to be able to say something about dxn zn, knowing that the limit as n goes to infinity of the distances between the corresponding elements of these two sequences goes towards 0. But the triangle inequality ends up getting us what we want here. The fact that this is true. See if you can complete it based off of this inequality, that the distance from xn to zn is less than or equal to the distance from xn to yn plus the distance from yn to zn. This should get you everything that you need to be able to get you what you're looking for. So try writing this out formally if this would help to kind of bolster this notion of this being an equivalence relation. So use the triangle inequality. Remember, this is something that is true regardless of the metric that we choose. This is a generic metric space. We're not just dealing with the real numbers here. Any space this would work for, any metric this would work for. And that's important in what is to come, that this is an equivalence relation, because we're going to be using this a good bit to talk about the completion of a space. So we now know that we can define the space of x bar to be the set of all Cauchy sequences in the original set quotiented out by this equivalence relation. So to be clear, giving this as an example, we would define the real numbers as the set of all Cauchy sequences in the real numbers, quotiented out by the equivalence relation given above. Here, S is the set of all Cauchy sequences in the rational numbers. This is how we would define the completion of a space. And in general, we could do this for metric spaces too. We are saying here that for any given metric space, you can define Cauchy sequences in that space. So you take the set of all Cauchy sequences and you set equal to them all Cauchy sequences that seem to be approaching to the same spot. That itself is the completion. This is a little bit strange maybe to think about because we don't think about the real numbers as sequences of rational numbers. But think about why we might do that. We don't have access to square root of 2 if we're starting with the rational numbers and attempting to construct something else. We can't just conjure square root of 2 out of nowhere because then I ask, how do I define square root of 2? And if I only have the rational numbers in my hands, then I don't know how to make square root of 2. You just make this funny symbol over the number 2. So I need to be able to construct it as something that belongs only to rational numbers. And Cauchy sequences of rational numbers never invoke square root of 2. I can just say, take numbers that go to a number that I'm going to be defining as the square root of 2. This is the number that I'm looking for. So we could even define a metric on this space to be hopefully that same notion of making a completion that we were talking about in our definition above, which is saying that if you have two equivalence classes of Cauchy sequences, and this is now Cauchy sequences, not necessarily these things that are for example, these are not necessarily going to be just rational numbers that these are converging to. This could be any Cauchy sequences. They don't have to be going toward the same point. They could be any Cauchy sequences out there. Then the equivalence classes of these things, the distance between them we will define to be the limit as n goes to infinity of the distance of the corresponding elements. So think the quotienting out is actually a really big deal here. Because remember, something about a metric is that if you have the distance between two elements is equal to 0, then your two elements need to be equal to each other. Well, think about how we defined the equivalence relation on this space of Cauchy sequences. The way we defined it is if the distance between the two elements, the limit of them, is equal to, of these quotient sequences is equal to 0, then, in fact, we are setting those two things equal to each other with respect to this equivalence relation. So that's extremely important here in this construction, is that we are quotienting it out by this equivalence relation because we need this first condition of a metric to be true. Namely, if you take 2 points and their distance is 0, they need to be exactly the same point. So now we need to go through and ask quite a few questions. And before we do this, you might think through yourself, what are the questions we need to answer based off of this? Even though maybe after having talked about it, it makes sense intuitively, there's still quite a few questions that we need to address to ensure that this is the right model to be using for a completion of this space. A few things that come to mind immediately are, one, is it indeed true that this is the case? Do I have that, for example, this D bar is a metric on the space X bar that I have constructed? It would need to be a metric in order for it to be a completion. So I need to go through the 3 conditions of it being a metric. Another thing I need to be thinking of is how does the original space fit inside of this set of Cauchy sequences? Note, I can't just say because the set of Cauchy sequences doesn't have the number 5 in it. How can I think of the rational numbers fitting inside the set of Cauchy sequences of the rational numbers? You may already have an answer to that, but that's another question I need to be thinking about because that's one of the conditions of completion. And then finally, I might start thinking about how do the operations work with Cauchy sequences? So I need to be thinking about all of these different conditions, and you'll see more as we go through and talk through these conditions, and that a lot of our upcoming slides are lemmas and propositions, and given with them proof ideas of how you might go through and answer each of these questions. So what I'll do is I'll go through and pose each and every question that we might try and throw against this construction of what we call the completion of the space X. Again, here, X is a generic metric space, and we are considering its completion here. So the lemma is, why does d bar xn comma yn exist for all xn comma yn? This is a really good question. Because why is it that when I have 2 Cauchy sequences, I can even take the limit between corresponding elements of their distances? If that doesn't exist, then I've not gotten a well-defined function, well, let alone metric, d bar. So I have to go through and answer that question first. If xn and yn are 2 Cauchy sequences inside of a metric space, I need to be able to claim that the limit as n goes to infinity of the distance between those 2 points indeed exists. And notice that the way that I go through and use that as far as a proof idea here is that I say, well, one, it suffices to show, since we are looking at distances of real numbers, that just suffices to show that the sequence dxn comma yn is a Cauchy sequence. So I go through and I write out dxn comma yn, dxn comma ym. And notice here how I go through and write this a little bit. I believe that this should be an n down here. So I'll go through and write that as a little bit of a change, just kind of to make sense of this inequality that I have down here. Because what I'm doing is I am taking something that's adding and subtracting the exact same thing to each of these values. And if I go through and apply a a triangle inequality to get to this point and an inverse triangle inequality to get to this point, then I notice something interesting. That what I have is the distance from xn comma yn to xn comma ym, which is the thing that gives me a Cauchy sequence here, that this is bounded above by these values right over here, dxn comma xn plus dyn comma ym. Notice that the way that these have changed is that instead of these being distances between 2 separate sequences, they are now distances between each of the individual sequences, xn and yn themselves, which we already know to be Cauchy by assumption. So this is only a proof idea. I don't go through all of the steps. Think about how you might go through and finish out this proof idea. How would I leverage the fact that xn and yn are Cauchy sequences to make these small enough to show that this is indeed a Cauchy sequence? Is our metric d bar well defined? So suppose, for example, that xn and xn hat are equivalent Cauchy sequences in our squiggly x, and that yn and yn hat are also equivalent Cauchy sequences. Then we want to show that the limits as d, x, and yn as n approaches infinity is equal to if I had replaced xn and yn with xn hat and yn hat. Here, note that xn hat and yn hat do not have to be different sequences. They sure can be different, but they could also be exactly the same. So for example, this is not only showing that xn and yn and xn hat and yn hat replacing both sequences work, this also works if I just replace one sequence in the xn or one sequence in the yn and keep the other one the same. We're just saying that these two things are related to each other. And due to equivalence relation, we know that every sequence is related to itself. So that at least gives us one thing that we could suppose is an equivalence in each of these. Well, how do we do this? Well, we, again, kind of use a little bit of a triangle inequality here. So this, once again, is a triangle inequality. To say that the distance from xn to yn is going to be less than or equal to, notice how I go through and introduce the xn hat and yn hat entries here. I'm essentially just saying, okay, if I'm looking at this in terms of absolute values, it's like I'm adding and subtracting xn hat to this value. But regardless, this is the triangle inequality invoked twice. The first and third terms on RHS are equal to 0 by, or at least go towards 0 by the definition of equivalence class. So maybe it would even be even better to say that these limit towards 0 as n approaches infinity by our definition of equivalence class. And this will yield a less than or equal to sign. And you can think about how you could get a similar argument to show that indeed this is greater than or equal to. Think I didn't have to start with xn and yn over here. I could have started with dxn hat and yn hat and done a similar breakdown in terms of a triangle inequality to make that work. Now we keep going. Notice that these particular next few slides are just going to ask us a bunch of questions, and we need all of these questions answered to make sense of a completion. You may remember from the reading, you were maybe surprised by how long it took to show that something is a completion of a metric space. And indeed, there's a lot of questions to make sure that we answer. So here's another lemma. Does it have the desired structure? Is x bar comma d bar a bona fide metric space? Because so far, all we've said is that the metric is well defined. We need to show that it is indeed a metric. That proof idea that I mentioned from before is saying that the equivalence relation is exactly what we need to show that the distance between two equivalence classes of Cauchy sequences is equal to 0 if and only if the two Cauchy sequences live inside the same equivalence class. The rest is just going to be kind of standard checking. At this point, you are allowed to just take representatives of each equivalence class because you know that if you had substituted out another equivalence class, you'd be getting the same limits by our previous lemma. So you can just go through and check and ensure that that's basically what works. Essentially, this is the very same type of structuring that we did for our exercise up a few slides ago. You'll notice that the spelling out the proof here is very, very similar. Indeed, you will want to be able to show that dxn, make sure I got it all right here, dxn comma yn is equal to dyn comma xn. But you'll notice that going through the proof of that looks very similar to how we did it when we had to do that for Cauchy sequences up above. Then there's a lemma, is the set the right size to contain X as a dense subset? Remember, this is one of our conditions of a completion. How are we going to fit, say, the rational numbers inside of the real numbers? What we're going to do is we're going to take constant sequences of those rational numbers. For example, we're going to take for 1/2, we're going to set that equal to the constant sequence of 1/2, comma 1/2, comma 1/2, so on and so forth. And because the x bar that we're working with is the equivalence classes of all of those, we're also going to be considering any Cauchy sequence that gets us to that point. For example, the sequence 0, 1/4, 3/8, 7/16, and then 15/32. That would be another Cauchy sequence that limits toward 1/2, but that would be inside of the same equivalence class as this. So we'll use the representative of the constant sequence inside of the set of Cauchy sequences. Then the set D, we're going to say the thing that we're trying to take the completion of embeds itself, that is, embeds itself as an isometry. So that is that there is a function I going from D to X that essentially is injective, and that metrics are preserved with respect to the distance between 2 points over here is the same as the distance between two images over here. That this set D, which we are defining to be just a set of all of these values here. So again, X bar is the constant sequence here. This is going to be dense inside of the set of all Cauchy sequences, quotiented out by this equivalence relation. Now, this is something interesting because the set of Cauchy sequences is huge. It's a humongous set. we're adding what seems to be a lot more than just constant sequences. We're adding a ton more, it feels like. And so because of this, we need to ensure that the set that we're building is actually indeed something that is dense inside of this. So here's a little bit of that proof idea. This follows from the case that X bar consists of Cauchy sequences inside of the original set X that we're working with. So it's eventually going to be close to an element of X. So for example, if I took something that's a constant sequence like 1/2, 1/2, 1/2, dot, 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 and I took another sequence, even if it was going toward an irrational number, right? Something like 1, 1.4, 1.41, 1.414, it might end up going farther and farther away from a sequence like this. But you might note that there's eventually going to be, regardless of how close you want it, some constant sequence of completely rational numbers for which this sequence gets arbitrarily closer and closer to. So again, think about the order of quantifiers here. You're saying that for all possible distances, there exists a constant sequence. That's important. Constant sequence of rational numbers that is close enough in metric with respect to that close enough parameter that you set beforehand. So think this is for all epsilon greater than 0, there exists an element d inside of d, a constant sequence, such that the distance between the sequence that you're working with, xn, comma d, that this is going to be less than that epsilon. And that's indeed something that ends up being true. Indeed, that's essentially what this proof idea is explaining. It kind of going through the set of quantifiers, it just ends up being something that makes sense. Think the rational numbers, you can always pick a rational number close enough to a real number. And then that same thing is true if you take a Cauchy sequence in this particular instance, 1, 1.4, 1.41, 1.414. Taking the difference between these two numbers, the limit between these two things is going to be very, very small as n goes toward infinity. So now we can think of the original set X that we're working with and D, this set of all constants, Cauchy sequences inside of X bar. We could think of these as the same space, with D being wedged inside of X bar. That's the isometry that I was talking about from before. In fact, this is a special type of isometry called an embedding, because it is an injective isometry. Now, a few more lemmas to ensure that we have all of the conditions that we're looking for, like, for example, that D is equal to D bar and things like this. Also, we need to ensure that this space is a bona fide complete space. Do Cauchy sequences of these Cauchy sequences converge to some other Cauchy sequence? That's a handful to think about, but that's essentially what we need to do. It's to ask the question, is X bar complete? We need to take Cauchy sequences in X bar. But remember that X bar itself is a set of Cauchy sequences. So these are Cauchy sequences of Cauchy sequences with respect to this D bar metric that we've been working with. So assume, for example, let's do a preliminary lemma that I'm not going to go through and talk about here. But assume that y comma d is a metric space and that d is a subset of y. If you take Cauchy sequences inside of d, the dense subset, and if they converge to an element in y, then y is complete. Notice that this is a slight relaxation of a condition that we ask for completion. Completion says Cauchy sequences in y converge in y. But this lemma says it's enough to consider Cauchy sequences in a dense subset D of y. Not all of y is where all of the elements that I need to be considering for completion do they need to belong. For example, this is saying that if I'm taking a look at the real numbers, I need to be able to say Cauchy sequences converge in the real numbers. I would need to take every possible Cauchy sequence of real numbers and show that that converges to a real number. This is saying it is enough to show that Cauchy sequences in Q converge in R. Cauchy sequences in the rational numbers that it converge in R. So think that's a big difference. Cauchy sequences in the real numbers can include square root of 2 in times of their Cauchy sequences. But this says if you have a dense subset, then you could just be replacing square root of 2 with a number that's close enough to it, and then just keep going. As long as those converge in the real numbers, then you have your original spaces complete. And that's exactly what we use for this lemma. Every Cauchy sequence in D, the set of all constant sequences that we've been talking about converges to an element in X bar. Since we know that this is a dense subset, we can utilize this lemma to answer the question, is X bar comma D bar complete? So indeed, that's going to be working out here. So our construction comes in clutch. It's a huge thing here. Can we find Cauchy sequences in D? Absolutely. All you're doing is you're taking sequences like, again, taking our constant sequence representatives for these classes. You're taking sequences like 1, 1, 1, then 1.4, 1.4, 1.4. These are all elements inside of D, the set of all constant sequences and their representatives. And if you take a look to make a Cauchy sequence out of these Cauchy sequences, that is, if you take the distances between corresponding elements here to be constantly closer and closer to each other, then what ends up happening is you converge to an element inside of X bar. And how do you do that? Well, the X bar element that you're going to be getting out of this is 1, 1.4, 1.4.1, so on and so forth. You're just going to take basically kind of like a diagonal argument. You're going to take the first element here, the second element here, and you're just going to keep going. That's going to give you something that is a X bar sequence that consists of that is a limit of all of these dense subset sequences, these constant sequences, the Cauchy sequence that's there. So that's going to be basically the proof idea here, is that you can take something that is kind of like looking at a diagonal argument of each of these things and get something that works. And that completes our theorem. Notice that even though I use the real numbers as an example to help make clear what was going on in each and every step of the completion process, that I never invoked something that said you had to take an absolute value or you have to be able to subtract two numbers. Notice that even with no operations given on our space, we have the theorem now that every metric space X comma D has a completion. These are all of the necessary questions that we need to offer to give us something that is a completion for this metric space. Again, I only went through and gave proof ideas in each of these steps just to kind of give more of a general notion of what we would need to do to show a completion of a space. Wasn't trying to go kind of too hard into showing all of the different techniques, because what I really wanted to focus on is what are the important questions we need to ask and answer in order to get to this sort of conclusion. If you want to see the more detailed proofs, go back to our reading assignment for section 3.7, and that should be very useful. So now that we've found a completion of a given metric space, we're interested to see what all is retained in completing a metric space. We know now that essentially the size of the completion could be humongous compared to the original set that you started with. So what properties of the original set are maintained in the completion of that space? Let's talk a little bit about continuous functions on our space. For example, can we take a continuous function on our original non-complete set and somehow make it and correspond it to a continuous function on the completion? So basically, we're asking the question of, do we retain enough information about the sets so that the functions that we get on those sets extend a little bit to the completion of those spaces and get us something that can work on the higher end? Well, the answer is no for the question of, can we do this for continuous functions? And let's be clear about some of the conditions that we're saying no to here. So the definition of an extension that I've been talking about before is saying that there is a way to write the function f, which is something that goes inside of a subset of a metric space, to another metric space, y. Then we would say an extension f tilde is a function that goes from the entire metric space, not just the subset, to that destination metric space, such that if you were to restrict the extension that you've made to the original subset, then you have the exact same function that you had from before. An example is you could take a function f going from 0 to 1 to r to be f of x is equal to x. But there's no issue in making an extension to that, taking f tilde of going from reals to reals to given the same formula, f tilde of x is equal to x. This is an example of an extension from the closed interval from 0 to 1 to the real numbers. If I restrict f tilde back down to the closed interval from 0 to 1, I still have the same function. The graph of this should also be a little bit illuminating. It's like taking a function going from 0 to 1 like this, and just allowing myself to extend it out onto a larger subset of the real numbers, or perhaps the whole real numbers itself. Any Anything like that would give us an extension of this function f. So the question is, could I extend a continuous function on this non-complete open interval going from 0 to infinity of real numbers, defined by f of x equals 1 over x, to the completion of it? Well, remember that the completion of this is going to be kind of like, think of it as like the closure of this set is going to be the closed ray going from 0 to infinity. However, there is no extension of f onto this closed interval from 0 to infinity such that f remains continuous. Now, notice, so just to kind of make another clarifying point here, we're not saying that you couldn't define a function on the closed interval from 0 to infinity such that when you take out 0, you still have just the original function f of x equals 1 over x. I could have gone through and said, okay, well, let's take f of x to be on 0 to infinity and define it like this. It's 1 over x whenever x is greater than 0, and 0 if x is equal to 0. That is an extension, but it is not a continuous extension, which I feel like is something that we need to be considering when we consider completions of x. Can we extend functions onto the completion of x such that the extension is continuous? Essentially, that's kind of telling us that the topologies of these two spaces work out very neatly. Because remember, continuity is something about openness in one, in the destination space, gives us something from the source space about openness of the sets that we were working with. Basically, if V is open in Y, then F inverse of V is open in X. So this is telling us something about the topology between these two spaces whenever these things are looking at continuity here. But it turns out not to be true due to this example. If I start with a continuous function on X, I may not be able to get a extension that is continuous. But perhaps we could use something a little bit stronger. What if we started with uniformly continuous functions? Let's let D be a dense subset of the metric space X, and let's let Y be a complete metric space. And let's let the function f be mapped from the dense subset to Y, and let's ask for it to be uniformly continuous. So you could imagine, for example, a function f that goes from the rational numbers to any sort of set over here, as long as it's complete. Then f extends uniquely to a uniformly continuous map, f tilde, that goes from x to y, x being the completion of the set D. Moreover, if f is an isometry, then actually so is f tilde, which is pretty cool. You get to pertain an isometry property here as well. So think about what this one means. This one says if I have a function that is uniformly continuous, then I can extend it to a uniformly continuous map. Think back to our original example. Kind of the issue with this one is there is no way to complete the graph of f of x equals 1 over x to be defined at x equals 0 in a sense, in a way that makes sense continuity-wise. And that's because it kind of blows up at x equals 0. So even if we're not including 0 in our domain, any open interval around 0, you're going to see points just going to keep going higher and higher and higher. The issue is you don't have controlled growth on your function. The function is not uniformly continuous. Remember that uniformly continuous functions basically get to work in a very specific way. If you give it a bounded interval, it's going to be a bounded function. So we start removing some of the issues that we have, like here with the 1 over x example. So let's take a look about what this proof is. First, for uniqueness, let's note that any two functions, so again, here what we're saying is that basically you cannot take two two extensions of the function, that there's only actually one that makes sense. And the one that makes sense is if I have a function f that's defined on a dense set, well, think about what's true about a dense set. Any sequence, any point inside of your entire set X can be reached to by a sequence of elements inside of the dense set. So if I define f of x to be the limit as n goes to infinity of f of xn, where xn is a sequence of elements in D, then this seems to define be a function on the entire space X. Again, any point inside of X can be reached by a sequence of elements inside of the dense subset D. So we could define f of x to be this limit. Indeed, if we're asking f to be continuous, this is the only choice. There's no other way to make this sort of thing work. The issue is, does this limit exist all the time? Well, remember back to when we had a previous homework assignment, which said that if you have that x of n is Cauchy, and f is uniformly continuous, so if f is uniformly continuous, Then whenever you have something like this, then in fact, f of xn is going to be a Cauchy sequence as well. And that's important because that means that we can define a limit of these f of x sub n whenever x sub n is a Cauchy sequence. And that's essentially the idea behind here of this particular proof, is that we're going to be making exactly this definition and this shows that these limits that we're trying to define exist. Note that we also need the completion of y here in order to say that these f of x sub n actually converge to some point inside of y. So this gives us a reason for the uniform continuity of f as well as the completion of y. Essentially, the rest of it is going through and showing that this is indeed an extension. And you might be interested to go through and kind of pick apart this proof a little bit, especially having gone through and talked about, after talking about our compactness definition there, where we talked about something called the epsilon over 3 argument. An epsilon over 3 argument is a very interesting one because it says, okay, well, is there a way for me to break apart different parts of this function so that it works neatly with this extension? You might notice the proliferation of things like epsilon over 3 all the way around in here. And that's because in order to get eventually to this epsilon at the very end, we need to be able to break apart and use essentially every single piece of information we have about the original function being uniformly continuous. We need the fact that f tilde is the limit of these functions. So there's a delta epsilon limit going on there. And we need to be able to pick apart each and every one of those parts here to show that f tilde is indeed a uniformly continuous function. That's essentially this part. This shows that f tilde is uniformly continuous. This sort of proof technique does come up quite a bit, so I recommend trying to break this one apart and see if you can find out what's interesting. Note all of the places that you need epsilon over 3s. For example, the original function f is uniformly continuous. So if you take two elements inside of your dense subset, then the distance between the y components needs to be small enough whenever the x prime and y prime values are small enough. Notice in particular, by density, we can also do the same thing for things inside of x, because you can always find a dense element that is close enough to it, namely delta over 3 close. So notice all of the different parts that are necessary here to make this sort of thing work. And try breaking this apart. It would not do me much justice to try and talk it through for you because there's just a good bit going on. But if you go through and read through it in depth, I think you can find a lot from that kind of in-depth reading. The last part of that proof is saying that if f is an isometry, so is f tilde. Essentially, it's saying that the limits of these distances make a lot of sense. And that's because the distance between any 2 points, even those not inside of the dense subset, are limits of points that are from the dense subset. Since the original function is an isometry, then the distances those are going to be between the images of those dense subset points are going to be the same. And that's exactly how we define the limit of f tilde x and f tilde y, their distance. A corollary of this fact, which is important, is that any two completions of the same metric space are unique up to isometry. And that's because we can make two embeddings into any two completions for the same metric space. Particularly the inclusion map of one x going into each and every one of these points here to either of the two completions, x1 bar or x2 bar, gives us something that's an isometry. By our previous proposition, I tilde then becomes an isometry when considering something going into the completion, x1 bar. Well, this is an isometry. In fact, it's an isometry that is injective, that you can go through and show that. It is also surjective because you can get any Cauchy sequence that converges to any point in the other completion that's going on here. So, in fact, we could even add a little condition here that this is a completions that are unique up to a bijective isometry. That means essentially if you have any two sets that are complete with each other, then you can put a bijective isometry between the two of them, basically saying that as sets, these are the same, and as metric spaces, their metrics are identical as well. And that's important to note. Is there another way to complete the rational numbers other than just giving the real numbers? Up to bijective isometry, no. Anything else that you could say is a completion of the rational numbers is really isometric entirely to the set of real numbers. So that does it here for us today. We've gone through quite a bit of construction. Hopefully something of that kind of struck your interest to help you search in a little bit further into these sorts of topics, because this sort of notion of a completion, although we focused on it with the rational and the real numbers, and we will do so in a homework assignment as well, is something that works regardless of the type of space that you're looking at. We'll talk about how we could look at different sets as complete, or if they're not complete, we could simply consider a completion of it. So that in some sense, the uniformly continuous functions on the non-complete spaces do still work on the complete spaces. That's something that you could see later on, essentially is saying, okay, I don't really too much care if my space is complete or not. I just want to know about uniformly continuous functions on this space. And if you do, then you say, okay, well, there's these unique extensions of these functions to the completion of this space. So with that loss of generality, we could just consider the complete space. And that might be very useful, especially if you have Cauchy sequences that you want to converge somewhere in your work. So we've gone through and talked about equivalence relations. We've talked about all the different steps you need to be checking for a completion. And then finally, we've talked about how uniformly continuous functions work neatly going from a non-complete space to its completion. That'll do it for me today. Thank you so much. Have a wonderful day.